Okay, so thanks everybody for joining today. And so today we're really delighted to have Professor Paolo Lipari from the Italian National Institute for Nuclear Physics and the Sapienza University of Rome to speak to us. So he received his PhD from the University of Rome in 1980 in particle physics, and then I believe a few years later made the switch into astroparticle physics and cosmic rays, working at the Gran Sasso laboratory, and became a researcher at the INFN in 1988 and subsequently became its research director, and has written many papers on a wide range of topics in high energy physics, gamma ray astronomy, neutrino astronomy, and recently also multi-messenger astronomy with gravitational waves. And in 2021, he was awarded the Galactic Medal at the 37th International Cosmic Ray Conference in Daisy in Germany. This is nice for me to hear. The late Professor Cormac O'Galactic was a pioneer of cosmic ray research who I know of quite well because he was at my institute, the Dublin Institute for Advanced Studies. And his estate established this medal with the Dublin Institute for Advanced Studies to be awarded by the Commission on Astroparticle Physics of the IUPAP for outstanding contributions to cosmic ray physics over a long period of time. So a career contribution to the field. So today we're going to hear a little bit of this, I guess. So he's going to talk to us about galactic resolved and unresolved gamma ray sources at very high energy. So please go ahead.
Okay, Jonathan, thanks a lot for the introduction. As I said, what I'm going to present some work, and unfortunately, this will be mostly phenomenological, as you will see. So this is the outline of what I'm going to talk. So I'm going to say a very elementary introduction and discuss the components of the gamma ray sky. Then I will discuss the source catalogs. And okay, well, we go. Then really have two parts. One part is about the spectral shapes of the sources and the cumulative source spectrum. And then I will address the question of the diffuse gamma ray flux and the question of separating the resolved and unresolved flux. So let me just go straight on. This slide is not necessary for you. This is just a classic image of the Fermi-Lat sky. So this is the gamma ray sky. This is actually at energy more than 100 MeV. And you know that the sky in the GeV and above is formed by an ensemble of point sources and a diffuse flux. And so actually, well, there are sources which are distributed in the galaxy. So the gamma ray sky, as you know, has a galactic and an extragalactic part. And in this talk, I will only discuss galactic contributions. And so this is just the emission. Q of E is the emission of all sources, all possible mechanism of emission in the galaxy. And it is natural to decompose this gamma ray emission, and you have a similar neutrino emission, of course, into a component which is called interstellar medium. So these are cosmic rays which propagate in the interstellar medium, they interact and generate photons. And then there is a contribution which is due to an ensemble of sources. And so the flux you receive, say I'm looking in a cone delta omega in the direction of delta omega. And so this flux will be formed by two components. So one component is a truly diffusive component generated by particle in the interstellar medium. And then there is an ensemble of sources. And some of the sources will be identified, will be resolved, and some of the sources will be unresolved. And it's in order to extract the interstellar part, I mean, you need to disentangle these two components. And I think this is an important problem. And so this is just some simple comments about the interstellar component. So this is, I hope you can see my mouse on the screen. Can you?
Yes, we can.
Okay, so this is the solar system, and if you look in a certain directions, you're integrating all emissions along this direction. So the flux that you're seeing in the direction omega is just this integral of the emission along the line of sight. And so you have a photon emission and a neutrino emission. In the case of the photon, you have to to include a high energy. You have to include absorption. But this is essentially would be a small effect for nearly everything that I'm going to say now. Now, this is just a comment, but I think to measure the interstellar emission is really very important for high energy astrophysics. And the reason is that the emission that you have, so this is an expression for the emission, and I'm just having like the leading component. So these are, you have proton-proton interacting. So there is a cosmic ray proton interacting with the interstellar medium, and then generating essentially pi zeros that decays into photons. So this is the dominant component. And so the emission is related to the spectral cosmic rays in the entire galactic volume. And so this is a way, an important way to study the distribution of cosmic rays in the entire galaxy. And this actually is crucial to understand sources and propagation. So I think actually to understand this is okay. So it's something which is important. And just to say, this calculation has three components. Well, you need to know the hadronic interaction. You have to know when a proton interacts, how many pi zero it creates or it has for subdominant models. And then you need to know the target. So you need to know the distribution of matter in the Milky Way. And what is important also, you have to know the space dependence of cosmic ray throughout the galaxy. And so this is actually the thing which is most unknown that you want to study. And so actually, I'm not going to discuss this. With Sylvia, we did two papers, and I'll just have some results about this paper published in 2018, where we discussed the diffuse gamma ray flux. And I'm just noting that, in this paper, we constructed two models. And one model is just a very simple, I think the most naive extrapolations. So we assume that the cosmic ray throughout the galaxy have the same, have a spectrum of the same shape in what is observed locally. And so actually you have a function. Actually, the distribution is has not the same absolute density, but the shape is the same. And so if you make this assumption, you can make a prediction. And so this prediction can be constructed. And actually, for example, in 2021, it was one of the first measurements of the diffuse flux at high energy. And actually, these are our two models. Now, a question which has clearly emerged is that it is important to address the question if this diffuse flux, these are measurements from Argo, these are measurements from Tibet, if this flux as a component of unresolved sources. And so actually to address this question, let me now talk a little bit about sources. And here I have 4 experiments which have created catalogs of sources. So this is the Fermi-Lat telescope, which I think you will know. This is the Hess telescope. This is Hawk, and this is LASSO. And so these are the catalogs which I'm going to discuss. Actually, in my title, I put high energy gamma ray sources. But I think actually it's important to discuss the gamma ray sources across the energy spectrum. I mean, there have been many papers addressed to discuss, say, TV gamma ray sources and now PV gamma ray sources. But I think actually that my point of view that you really should discuss the entire spectrum because you want to know if there are transitions between different classes of sources. You want to follow these transitions and understand what it is. So Fermilab now has collected a large number of sources. The last data release contains more than 7,000 sources. At higher energy, you have a much smaller number of sources, but I think actually that these sources are very significant. As you know, the Hess Cherenkov telescope has observed, has made a survey which is in a limited part of the sky. So this is galactic latitude near the disk and this range of longitude. And there are 78 sources in this catalog. And Hawk has measured 65 sources in the third catalog. And recently, I mean, approximately 1 year ago, the LASO detector has produced a catalog that contains 90 sources. And actually, well, this is just, well, an important thing is you see, the Hawk and LASO telescopes are air shower array telescopes. This is an important consequence. And the important consequence is that the sensitivity, while for Hess, you need to know the program of observation of the telescope, you know, where it looked at. But for an air shower telescope, you don't need to do this because the sensitivity of the telescope is entirely determined by its position. So its geographical latitude, and then sources will move in the sky in a well-defined way. And so actually, these two detectors see the sky through whatever sky they can observe in, I mean, around the zenith angle. Well, actually, an important thing is, well, LASO has two components. So there is, this is just an image, it's an old image, but the concept is that you have a Warren-Cherenkov detector, which essentially is sensitive from TV to in a range of the order of 10 TV or so. And then there is an extended square kilometer array, which is sensitive above 10 TV and reaching 1 PV. And so actually the ensemble of these two detectors allow to study the sources in a quite broad range of energies. And so actually you see that the sources, the WCDA, the Warren-Cherenkov detector, a lower energy, measures 69 sources, and the square kilometer measures 75 sources. And actually, it's interesting that of these sources, 54 have been detected by both instruments, both sub-instruments of the telescope. And so for these sources, you have a spectrum which extend in a quite broad energy range. And so now, something which I think is important is that you have an ensemble of sources. So J is an index around the sources. And so you can sum over all sources, and then you get a cumulative spectrum, the spectral shape of the ensemble of the galactic sources. And then you have a set of spectra of individual sources. And I think actually it is important to understand both what is the spectrum of the ensemble of the sources, and then to understand the spectra of individual sources. And this is, and actually, let me just, this is a slide which contains some important elements of what I'm going to discuss. And so actually, let me just describe what it is. This is the energy in GeV. So it goes from 1 GeV to 1 PV. And so this blue line is the sum of all Fermilab sources. Actually, these are, I've only selected a region, actually I've not written, but this is the same region of the Hess detector. So this red line is the sum of the 78 fits of Hess. And this line is the fit of the 65 sources of Hawk. And these two lines, this dash line and this dot dash line, these are the sum of the, well, I've eliminated in the LASO in the LASO telescope, there are 4 extragalactic sources, 4 known AGNs. So I've eliminated those. And so this is the sum of the WCDA, so the TV and tens, 100 TV sources of LASO. And so actually, you see, it's interesting. And for the Fermi spectra, I've separated the contribution of pulsars. So pulsars are the brightest sources in the Fermi-Lat catalog, and these spectra are mostly fitted with a super exponential cutoff. And so actually, you see that the overall spectra of the galactic sources has a shape, and this shape has a quite interesting result that you see. This is a spectrum multiplied by E squared. So the spectrum starts quite hard and then actually softens quite dramatically at an energy of the order of 20, 30 TeV. And actually, you can see that from TeV to 10 TeV, the 3 results of Hess, Hawk, and LASO are actually in reasonably good agreement. And this actually is a spectrum of the order of minus 2.7. And then the spectrum softens. And I think I think it's a very important point. But actually, I'm afraid that I will mostly discuss experimental results in the sense that I think this is the question that should be understood. And actually here I have one line, and this line actually is a calculation from the diffuse flux we calculated in 2018 for this region of the Hawk results. So actually, this it's interesting that the sources and the diffuse flux are approximately of the same order. And so actually, I think one of the things that you want to understand is why the cumulative spectrum of all galactic sources has this shape. And okay. If I cannot, if you want to interrupt me and make comments, please do, and let me know. So actually, this is again the spectral index of this spectra that I have shown that I've shown before, and actually you can see that, well, from one, so the Fermi sources are quite hard, have a spectrum of the order of e to the minus 0.2 or something like this. This is the Hess spectrum, and this is so these lines are the global spectrum of measured by LASO WCDA, the Warren-Cherenkov, and this is the spectrum measured by the square kilometer spectrum of LASO, and this line actually I will discuss is the spectrum of the sources which are measured by both detectors, and so this is let me make a so these are spectral the functional forms that have been used to describe the gamma ray sources. And actually, let me say, these 3 forms, power law, log parabola, and a power law with super exponential cutoff, these are the 3 forms which have been used by by Fermi. And the Hess telescope has used either a power law or a power law with an exponential cutoff. And Lazo and Hawke fitted the results with a simple power law. And the comment, I think it's very interesting that actually most of the sources which are observed by Fermi are described by a curved spectra with this form of a log parabola. And so the log parabola is the spectral index, which is given by this expression. So the spectral index for log parabola is grows logarithmically with the log of the energy. And so actually, this is the form, sorry. So this is the form of the spectrum. Actually, it's interesting that this is one, you can rewrite the log parabola has a Gaussian in the logarithm of the energy. And I think actually this is, if you try to understand the mechanism that generate the spectrum, this could be a form which is more apt to interpret the origin of this spectrum. And so this is well, this is just an image of the sources of Fermi, and again, this is just a few that you have. You can clearly see an isotropic background from galactic sources, and then you have an excess of sources along the galactic disk. And actually, this is the fact that you see the disk. Actually, it just demonstrates that the horizon on which you observe sources is actually much larger than the thickness of the disk. And in fact, of the 7,000 sources of Lazo, of Fermi, there are of the order of 1,200 which are of galactic origin, and actually, well, this is just a decomposition of this. Let me just this is just to show again that you have that the galactic sources for Fermi have actually so these are also you have an AGN contribution, and you see the AGN contribution is small on the galactic disk, and then actually it's not completely trivial to extract the galactic source population from Fermi, because you have many sources which are not identified. But actually, you can see that the non-identified sources in Fermi have a significant galactic component. And again, this is actually the longitude distribution of Fermi. And again, you see, this is actually selecting the disk. So you select 3 degrees of galactic latitude. This is the longitude distribution. And actually, some remarks is that, well, actually, first of all, you have an excess of sources in the direction of the galactic center. This actually is very relevant for several discussions about galactic center excess and so on. But an important thing is, again, that you can see that you see an excess in the general direction of the galactic center. And this is, again, it's an illustration of what is the horizon of these sources. And also, and this is interesting, you clearly see evidence for spiral structure. So you have this, this distribution is not smooth, revealing a complex space structure of the sources. And this actually, again, this is the component. So you have a large effect of pulsars, and then you have actually, this is just a fraction of the flux, and you have a contribution of pulsar wind nebula or and pulsar combination of pulsars and object supernova remnants. So you have this contribution that start to enter in the when you approach the TV energy range. Okay, so the point, this is a point that I wanted to make. if you see the sources of here I'm selecting sources in the disk. And so in the disk, you see that the sources have a quite, well, the power loss, most of the spectrum is generated by log parabola spectra. And these log parabola spectra have significant curvature. So you see that this the change, these two histograms are the same sources with the slope measured at 1 GeV and at 10 GeV. And you see that the spectra softens by, on average, 1.44 of slope. So all the spectra are curved. And I think actually that this is a crucial challenge for the modeling of the sources, to understand why the sources are curved, what is the origin of this curvature, how you can model it, understand. And actually, this is another result. And the result is that different sources contribute a different energy. So I've discussed that roughly the spectrum of the Fermi sources has the global spectrum as a spectral index, which is of the order of 2.2, 2.3. This is the sum of spectra which have different forms. So actually, this is just selecting a region in the disk. You can see that these are you see these darker lines are the 5 brighter sources at 1 GeV. And these red lines are the brighter 5 sources at 10 GeV. And you see actually that the sources which are bright in the 100 GeV are not the sources which are brighter or lower energy. And so the spectrum that emerges at the cumulative spectrum is not the spectrum of the sources, but is a combination. And so you have a gradually changing population of sources across the energy range. Okay, after this comment,
excuse me, may I ask?
Yes, please.
May I ask a question about the previous slide?
Yeah.
So for sources which are identified, I guess this kind of curved spectra is what you would expect for pulsars. So can all of these sources with curved spectra, some of which may be unidentified, is it reasonable to attribute it to pulsars, or?
These sources are, most of the sources are, you can identify them as pulsars or pulsar wind nebula better, but also supernova remnants have curved spectra. And also the binary, I think there are essentially 3 major contributions to the galactic sources in Fermi-Lat. Well, there is a pulsar emission, which stops at a few GeV. And then you have 3 main contributions. And one is pulsar and pulsar wind nebula. Then you have supernova remnants. And then you have a third component of binary objects. And all 3 of these contributions have curved spectra, I think. I think the presence of curved spectra, it seems to me as a universal feature. And I think, well, actually, one of the things I wanted to discuss, I really think that understanding curved spectra is a central challenge for modeling, well, the sources and probably also acceleration. This is one of the points I want to make.
Okay, thank you.
Other comments?
Okay, if you started these comments, maybe we should do that later, but let me just, I have a comment. Hi, Paolo.
Hello, Felix.
Felix.
Hello, Felix.
So I think we should be a bit careful to mix all Fermi sources, because they could have quite different nature, and of course they are quite different nature. So for pulsars, more or less we know the spectra, and pulsars, not pulsar in nebulae. And that is the typical curvature spectrum, which is curved after 1 GeV. What concerns the extended sources, that is more complicated because there are three types of extended sources. Basically, could be pulsar in nebulae, supernova remnants, mid-age supernova remnants, and the clouds, which are echo of these past sources, supernova remnant sources. And now we know another new class, this is stellar clusters, which are continuous injectors. So supernova remnants are solitary events. So each of them, they are so sensitive. Even you have the fixed energy distribution of the injected spectra. Even that could not be the case. This is very depends on the environment. Like in supernova remnants could produce different type of the spectra. But even we assume they are the same. For this type of sources, propagation plays a great role, and that is almost unpredictable. How could appear this spectra? For example, for the molecular clouds, depending on the size, age, distance from the accelerator, which already gone, we could expect any spectrum. The same is less for pulse stellar cluster. So I just want to say, sorry, I went too long.
No, okay. This is, thank you, Felix. Thanks a lot. Well, essentially, here I'm just being the interpretation of all of this. I think actually even in then I'm now entering to discuss higher energy, but I think also at higher energy, I think you could have multiple contributions. You can try to explain as a single dominant class, but this is not obvious to me. But let me go further.
Sorry, I think maybe you should not interrupt.
But that's absolutely relevant. So I just wanted to show, entering now, actually Lasso, Felix is one of the important authors of this paper, which is actually remarkably important. And so actually, 69 sources measured by Lasso have been fitted as power law fits with a pivot energy of 3 TeV. And 75 sources have been fitted with a pivot energy of 50 TeV. And 44 of these sources are seen about 100 TeV. And I think actually it's quite interesting that 54 of the sources are seen both in the TeV and, let's say, call it multi-TeV energy. And actually, see, these are the spectral index of the WCDA and of the KM2A kilometer square slopes. Actually, the same plot is in the catalog paper of Lasso. But actually, you see, it's very interesting that, well, I think there are two things to note. One thing to note is that these distributions are both quite broad. So there is not a single slope of the sources, but you have a broad range of slopes. And then also that the slopes are quite different. So there is a significant difference of more than 1 unit of slope. So at high energy, the sources are significantly steeper. And actually, here I'm plotting. This is a scatter plot of the spectral index of the 54 sources, which are seen both at low energy and higher energy. And so actually, you can see clearly that for just one exception, for 53 of these sources, the slope at higher energy is significantly larger. So all spectra, with except of one, but this one actually is not very significant. This is nearly a flat spectrum. You have a steepening of the spectrum. And so actually this I think is one of the most relevant elements of the discussion. So the spectra seen by Lasso have have a significant softening. And so actually that's why I was discussing before. What is the nature of this softening, and what is the structure of this softening? I think this is a question. And in fact, I've been asking myself this question. I would like to discuss this with Felix and all of you. I don't have a good explanation, but I want to stress that I think this is quite important. Actually, let me just show, this is just, I'm not showing all 54 sources. I've just shown a random number of them. And actually, you see, for each of these sources, you have two power law, one at lower energy and one at higher energy. And so actually, to power law, they always, by construction, they have two straight lines and they cross. And so actually, you see, actually here there are three lines. This dashed line are all galactic sources seen by the water Cherenkov. These are all sources seen by the square kilometer. And actually, you can see, actually, this is a very interesting thing. You see, the spectra, so the sources have a broad range of slopes, but the cumulative contribution is actually a quite smooth power law. And the same things as at higher energy. And this blue line is the sum of the 54 sources, including like a knee at the point where the two fits cross. And I think that actually this is one of the features. I'm really sorry, I'm not offering an explanation for this. I'm just pointing out as a crucial, important element that should be discussed. And actually you can see that the combination of these 54 spectra, the ensemble is very similar to the other two. I think it's very likely that also the sources which are not seen, in fact, actually, they are not seen because the spectra has a bend. And so this is one of the things you want to understand. You want to understand why the spectra softens. And here actually is like, if I make, so this blue line, if I make is spectral index, this is the spectral index of this line, which of course is all discontinuous because you have each element that enters. And so you have all these contributions. And so you have a spectral index that goes from something like 2.7 to 3.4 across an energy range from like 10 TeV to approximately 100 TeV. And so this, I think, is one of the things which should be understood about the nature of this of these effects. And this is again the same results. So this is the distribution of break energy. And so the break energy is in this range. Most of them are from 10, 20 TeV to 100 TeV. And this is the size of the spectral break. And these are the distribution of the two things. So this is a feature which I think is quite important. Incidentally, this is important because this presumably also the unresolved flux will have this shape and should be understood. So actually here I have a comment. This is really a terrible speculation, but I think it's, if you look at this result, this result, that many spectra, actually one of the questions, if how you describe the spectra. Actually, I have one of the spectra, actually the crab, which actually there is a log parabola fit, which is published by the data. So you probably, this is just, so the question is how you describe this softening. And so here, similar things happen also for extragalactic sources. I wrote one paper a few years ago, and actually, I'm really asking myself if something similar could not possibly happen also for cosmic rays. So you see in cosmic rays of the Earth, they have a slope, and the question is this a fundamental universal spectrum, or is it just a statistical combination of spectra of different shape that contribute to this? And I think this, for me, this is a question that I found very intriguing. if the observed slope of cosmic rays is the reflection of some statistical effect. And this is just a comment in general. The origin of power law there are power laws everywhere, and their origin not only in cosmic rays. Power law is explained as Fermi acceleration, but there are many power laws in nature of different origin, like earthquake and so on. And so actually I'm asking myself if the cumulative spectrum has the cosmic ray spectrum originates from a statistical effect, which is, this does not mean that Fermi acceleration does not exist, but that the construction of the spectrum is more complicated than the textbook explanation that we give. And okay, so I'm kind of a little bit behind my time. I now want to address a little bit the question of resolved and unresolved flux. And in order to calculate this question, you need, of course, essentially you need like this quantity. So you need the distribution of sources in terms of, so this DNS, this is the distribution of sources in terms of position, luminosity, and morphology. Here, I make a minimum model of the morphology, has the linear size of the sources. Oh, sorry. Okay. So anyway, so this is the flux. The flux of the source, of course, is linear with the luminosity of the source, and then goes like 1 with the distance squared. So in order to calculate the flux for the ensemble of sources, you just have to integrate in the appropriate volume, and then over all the distribution. And so this is the total. So the total. Note actually that when you calculate the total flux, you are insensitive to the luminosity distribution, but you're only sensitive to the total luminosity of all sources. And for the unresolved sources, you just have to cut this integral, selecting only the faint sources. And so actually, so now to calculate the unresolved sources, you really have 2 elements that enter the calculation. Well, one element, you need to understand the telescope. So you need to know what is the minimum flux, which is a function of direction, and of course is linear with the luminosity. Will depends on the morphology of the source, but so you need to know the telescope. But most importantly, and this is the real problem, you need to understand the distribution of sources. You have to construct a model for the distribution of the sources. And so this is actually, I think, can be a very complicated problem. And an hypothesis that simplifies the problem significantly is, of course, the factorization hypothesis. So you assume that the distribution of sources, the luminosity distribution of the sources is the same in all points of the galaxy. And similarly, now, I think actually this factorization hypothesis is to me, certainly incorrect at some level, but it's difficult to avoid this. I think future studies I think actually what will emerge eventually is that there are different classes of sources that contribute in different ways, and they have different they have different dependence of energy, and they have different space distributions, and you could have also different effects. So the sources toward the galactic center could be different from the sources away. But let's assume the things. And so actually, the basic idea that we've been using in order to estimate the unresolved flux is outlined here. So we assume the validity of the factorization of the sources, and we assume, well, to avoid we assume all sources of the same size, and then you can change the size. And then you adopt a space distribution. And to adopt the space distribution, there are distributions which have been published for pulsar, supernova, and models of the spiral structure of the galaxy. And then you can assume or assume a form, a parameterization of the luminosity distribution that depends, for example, on a few parameters. And then you can try to obtain information about this luminosity distribution and therefore the fraction resolved and unresolved from the angular distribution of the observed sources. So this is the idea. So let me be offensive a little bit and outline the idea with a really trivial model. So here you have, here the galaxy is just a homogeneous disk. So this is the sun. And so there is a density of sources. Let's say now for the moment that the sources are all identical. So the luminosity distribution, you just tell me what is the luminosity of the sources and what is the total luminosity of the galaxy, or the density of luminosity. So if I look, say, in two small cones in the direction A and in the direction B, and then I will see a certain number of sources, if the horizon, so this line is the horizon. So if this is the horizon, in the direction in the cone A, I will see a number of sources that goes like the horizon square. T is the horizon for the detection of the sources. In the direction B, of course, I'm saturating the horizon. So the sources in B are just proportional to RB squared. And note actually that the flux, the total flux of all sources, resolved and unresolved, is actually proportional to the logarithm of the distance. So actually this, yeah, so the total flux is logarithm of RA. The reason why the number of sources grows like T squared is, of course, because you have the number of sources grow like T squared, but each source has an effect which is 1 over T, and so therefore, when you're integrating, emerge a logarithm of T. And so the fraction of resolved is just a logarithm of T. And so this is actually now the idea. If I compare NA and NB, so the ratio of NA and NB, you can obtain the horizon of observation. And actually from the horizon, you can immediately understand what fraction of the total flux is resolved. And since you see a part of the flux, you can estimate the unresolved flux from this result. And so the ratio NA over NB, assuming that the horizon is the same in the two directions, tells me what is the horizon of the sources, and then this tells me what is the resolution, the fraction which is resolved. So this is the elementary geometrical idea. So actually from the horizon, then you can estimate the luminosity and then also the total luminosity. So this is the fundamental idea that you can, and so here I've done this game for identical sources, but you can put a luminosity distribution and do the same game. And so actually here, when you apply these results to a telescope for extensive Earth shower array, you have an interesting, it's an obvious geometrical element, but this is, I think, important. I will spend just 2 minutes describing this, even if it's obvious. So this is the observer, which is at a certain latitude. And so actually, you see, the sensitivity of an Earth shower telescope is completely determined by its geographical position. And so actually, the telescope will see a region of declination, which if you observe, so actually, you see a source which has a declination equal to lambda, the geographical latitude, that's the source which will culminate at the zenith. And then actually you will see only sources which pass at an angle theta max from the zenith. And so you will see these regions. And so actually, what is the implication? The implication is that, So this again, this is the celestial equator. So and this is the galactic disk, which is inclined by, I think it's 66 degrees or so on. So actually, if you divide the sky into two parts, which are, you see, left and right of this critical longitude, you have identical sensitivity in the two sky regions. So this is the idea. Let me just illustrate this for LASO. So this is actually the sky over LASO. And so LASO has a latitude, I think, of 29 degrees. And so actually, the region of the sky observed by LASO is all this shaded region. And so you do not see a region around the pole, and then you do not see this region here. And actually, it's interesting to note that you know, the region A, more toward the galactic center, and region B have exactly the same exposure. And so the difference in number of sources in region A and region B is entirely due to the fact that there are more sources in region A and less sources in region B. And the ratio, actually, sorry, here I have these 4 points are 4 AGNs, which I'm now considering. And so actually it's interesting to note, first of all, that actually all this dashed line is declination equal to the lambda of the detector. And so actually you really see the disk, but this is significant. So this actually tells, so the fact that there is this asymmetry, that there are more sources in region A than in region B, is just an indication of the fact that the horizon is significantly longer than essentially the extension of the galactic disk in the opposite direction. So this is actually, so these are these two regions effectively. You see the exposure in these two regions, these two regions are equal in solid angle, and this region sees a larger part of the galaxy. So from the analysis of these two results, you can estimate the have a measurement of the horizon, and from the measurement of the horizon, you can make an estimate of the unresolved spectrum. And actually, this is just you see, for here, if I'm integrating over this entire, divide the sky in two parts, these are the ratio. You see, these are for Hawking the same things. You see an excess of sources toward the galactic center, and this gives an information about the length of the horizon. And from the length of the horizon, if you assume that you know the geometry, then you can determine the resolved fraction. And here I have some additional numbers. So and then you can proceed to do these things. I think I should rush toward the end. So actually, one of the questions is to interpret these results. Actually, note, I think there is an interesting point that I would like you to notice. If you look at these two parts, you can clearly see also qualitatively that the distribution in latitude of sources in region B, so in the region toward more to the galactic anticenter, this is broader than toward the galactic center. So actually, there is an asymmetry in the spiral structure of the galaxy toward the galactic center and against, which is, so you need to model the geometry correctly to play this game appropriately. And actually, for example, we have tried to construct and discuss the spiral models. And okay, so we can use this is when you do this, you need to know how the sensitivity of the detector change with declination. And so actually, these are the description of the lasso and Hawk for as a function of declination. You're most sensitive for particles for sky directions that pass through the zenith, and this is actually the region of the galactic disk that are observed by the two detectors. And so you have to include a description of the luminosity distribution, and this is a form which has been adopted in several works, in which the distribution is a power law in luminosity with a sharp cutoff. Here I'm using an exponential cutoff of the luminosity. So you have this, this is a 3-parameter model in which you have a total luminosity of the galaxy and a characteristic luminosity. And then you have this exponent, which essentially controls the relative importance of high luminosity and faint sources. So actually, in this model, you have that the number of faint sources diverges, but the total luminosity and the total flux, of course, remains finite. And the total luminosity and total flux actually is dominated by sources which are luminosity around the maximum luminosity. And so actually, one important point is that if I go back to my toy model, is that the ratio from looking in the two directions, A and B, is in the case of identical sources, is simply the total number of sources which are in two angular regions. But if you have a luminosity distribution, this the effect of the is suppressed, because the number of resolved source, when you increase the horizon, you increase the number of near sources, and so you have this behavior is suppressed. So this, let me just make a more concrete example. If the ratio, this is now for the region NA and NB of lasso. So if I increase the horizon, the ratio NA over NB, and this for a certain model of the galaxy, grows to a factor of 10. So there are there are 10 times more sources in the region which is more toward the galactic center than toward the galactic anti-center. But if you have a luminosity distribution, this ratio saturates at a lower level, and this also depends actually on the size of the spectrum. If the sources are more extended, you have that a larger number of sources is not resolved, and so actually from this you can extract you can pass from luminosity from horizon to luminosity, and this is actually the experimental data. So from the distribution you can obtain information about the luminosity distribution, and then you can pass from this to an estimate of the resolved flux. So this is the idea, I'm trying to finish and have some questions. So this is actually are now the measurements of the diffuse flux which have been obtained by Hawk. These are the measures of Tibet, which shown before. These are the measurement of Hawk, and this is a measurement of lasso. Actually, it is unclear to me how much this is entirely consistent. So these lines are actually were the prediction of 2018 for this flux. So let me just make an example of this exercise. So this is the publication of Hawk, and so they are looking in this sector of the sky, and so this is actually our old sources which are in the sector of the sky, and this is the sum of all sources in this region, and this is the diffuse flux. Now, actually, it's interesting that for the source flux, you can assume that this is all unresolved sources, and so you have a maximum power for all sources. On the other hand, you can try to estimate on the basis of this measurement what is the fraction of that can be unresolved on the basis of this geometrical argument. And on the basis of geometrical argument, you find that probably only that you are observing more than 1/2 of the resolved flux. And so this diffuse flux has a significant contribution from interstellar components. Okay, and so actually here are the same. You see, these are integrating from 1 to 10 GeV. Here the resolved fraction is the resolved source fraction is 1/2 of this diffuse flux, and so actually this allows you to determine a range of luminosity, and you can try to estimate this on the basis of this argument, and you can try to do the same things for lasso. And here actually it's again these lines. So you have these two regions, the inner region and the outer region, and this is the contribution of the sources. And so you can try to do this. I'm not going to enter. I think a discussion of the numerical estimate it will actually we are still working some a numerical analysis, but again you can let me just you see actually this is again from the ratio of sources in the two regions, you can map the fraction of the unresolved flux over the total source flux. And so actually you can then either make an absolute calculation, so combine with the resolved flux. And so from this, you can make different sort of estimates of the flux. And the thing is that actually the conclusion is that you are in a difficult situation where the components of unresolved and interstellars are comparable given the uncertainties in geometry and other property of the sources. I think there is an opinion of several colleagues that unresolved sources dominate the diffuse flux, and I think this is actually is questionable. So anyway, let me take one more minute to summarize the main points that I wanted to make, and I have two parts in the conclusion. The first part is again these qualitative results, and I think this for me is an important point. So the cumulative spectrum of all galactic sources undergo this significant softening in this range, with a spectral index that increase of approximately 1 unit. And you have to understand why it is so, and if this is kind of an extended break or a more uniformly curved spectra. And actually, this actually implies that the spectrum of the cumulative spectrum of the sources is not very dissimilar for the diffuse interstellar flux, which perhaps is intriguing. And this is actually what makes the separation difficult, that the energy spectrum are not too different. And then actually, this is another point. Not only the cumulative spectrum has a softening, but essentially all spectra in this, which are measured in this high energy range, have softenings or curvature. And so you have, so the curvature is not only, and it is something that has to be modeled. And another thing, the spectra of individual sources have a broad energy range, have a broad, can change significantly. And so if you have universal mechanisms that are operating, there are variables that generate a large range of spectra, and you have the challenge of describing them appropriately. And then on the second part, on the resolved and unresolved flux, I think the game which I think one should play, obviously, is that you are now seeing a significant number of sources, and you have to use the sources to generate, to extrapolate and generate the unresolved spectrum. And I think actually that this geometrical idea to measure the number of sources in different angular regions is important to do this. But one of the uncertainty is that you need to know the space distribution of the sources, and actually, in particular, understanding spiral structure is not a negligible problem. And so this is the bottom line, which I'm afraid I will leave it. But the point is that given the uncertainty, I think these two contributions of interstellar and unresolved are given uncertainties are comparable, and so a critical discussion will we are planning to complete this, but it's difficult. But I think actually, to me, it is hard to make a sharp declaration a way or another, and to make a critical discussion. Okay, I'll stop here. I hope I was understandable and not too boring.
No, not at all. No, thank you very, very much for this really brilliant talk. Greatly enjoyed it.
As I say, I apologize. I feel a little bit guilty toward my colleagues of being so data-driven, but I think I wanted to collect some elements on top on what theory must be constructed, which hopefully will go ahead in doing it.
Oh, great.
Felix, I know that you will have many criticisms, and
so there's
no, Paolo,
already.
Great talk. Sorry, it's just his topic is so complex that
yeah. I think anyway. I think the Lazo result is certainly fascinating. But I think you really should put everything together, starting also from the Hess spectra are also very interesting. I had one part which I have eliminated just a short time ago, but for example, you see the Hess spectra. One question which is very interesting is cutoffs. The Hess catalog estimates some cutoffs. I think some of these cutoffs are really just interpreting curvature, and some of these cutoffs are actually better fitted by me with log parabola, a more regular curvature. But some are cutoffs. But actually, also, if population changes across the energy spectrum, then also the presence of cutoffs is very interesting. Even in the Fermi result, it's interesting that essentially all sources with the cutoffs that SERPS observes, exponential or super exponential, are in the GV energy range. At higher energy, Fermi always observed spectra which softens gradually, and I think is also this is significant.
I
There
see
are
we.
questions, Jonathan.
Sorry?
There are questions.
Yes, I see that. Thank you. So first question was Susumu Inoue. Please go ahead.
Yeah, thank you. So I guess related to your last point, I remember the discussion that occurred during the first LASO symposium last May when you were participating remotely, and you raised the point that when you're talking about cosmic ray induced interactions or emission, there's no clear definition up to which region this should be associated with the sources and from where it's the diffuse. It should be more associated diffuse. So today, I guess you had a more phenomenological discussion without discussing the origin. But I saw that so when you're discussing the LASO contribution from the inner galaxy, the contribution from the individual sources seem to be already in excess with the what LASO mentioned as the diffuse emission. Is this correct? Maybe if you could go back to the slide.
Yeah, thank you. This is a very good point. Okay, yeah, I think this is the slide. Let me.
Yeah. Yes. So.
Well, yeah, actually, you can see this. This is very. You're pointing something. If I look at this, you see this is a diffuse flux by measured by LASO, and this is the sum of the fluxes, which actually are nearly a factor of 2 higher than this diffuse flux. And so actually, this seems to suggest now. If I try to estimate what is the unresolved, if this is the resolved flux, the unresolved flux, I think is probably 1/2 of this. Because, and so actually, because the point is that given the horizon that you infer, you are resolving a large part of the flux. But the question is, well, I don't want to, one problem is that this flux, this is not really consistent because the LASO flux is obtained after masking the sources. And so this actually, I want to make a comment. Masking, when you do this exercise, masking the sources is also masking the region of the galaxy where the diffuse flux is larger, because they're correlated. So actually, I think that these results should be multiplied by at least a factor of 1.5, and so it's but this is actually another thing is that so yeah a critical and a point. Let me just wanted to show. I'm really worried about this discrepancy between the LASO result and the Tibet result, because these are, they're not the same angular region, but they're very similar. And so I think I really would like to clarify the experimental situation about why the points of Tibet and the point of LASO are so significantly different. So these black points and these blue points are essentially in the same angular region. So and another thing is it's interesting. You could have a different behavior in different angular regions, because in the outer galaxy, then you have the diffuse flux is larger than the source flux and than the resolved source flux. But and probably the unresolved source flux is still, it does not add up to arrive to here. So a critical discussion is not easy, and I think also to put together everything, it requires some care and a critical discussion.
Yeah. Okay. Thank you very much.
Thank you.
Okay. Another question from Dimitris Semikos.
Yes. Hi, Paolo.
Hello, Dmitry. Hello.
I just have a question concerning. First, I wanted to comment that I think the neutrino flux would be crucial to distinguish this, because diffuse, true
Absolutely,
diffuse would
very
be
good,
neutrino.
Dmitry. I should have said that. Yeah, of course, because the interstellar would be of hadronic nature, and therefore would be
Yes.
neutrinos. So already the
most-
ice cube results is significant in this respect.
And most of lasso sources are pulsar wind nebula. At least big fraction of lasso sources is pulsar wind nebula, so it would be leptonic mostly. So and I have a question to the way you calculate this flux, because the galactic disk is finite small size, and the sources are located in the disk. So when your tube is coming very far in outer galaxy, it could exceed the size of the disk. So the calculation of how many sources you have would be violated at some point. Did you take into account that the width of the disk with sources is smaller than the size of your viewing angle at some point?
We are trying. Well, first of all, thanks for the remark about neutrinos. I should have discussed neutrinos and mentioned this. So this is a very important point. So in this sense, you can a neutrino measurement will measure. Well, actually, a question which is I think I would not. I know that some of my colleagues assume that most of these sources are all of leptonic origin, and I think this is likely, but on the other hand, the diffuse flux is certainly going to be hadronic, and so the neutrino measurement is significant, and the ice cube result is quite interesting, and a complete discussion should include that. About I think the geometry, the geometry, you need to, when you do these exercises, it's very important to have a realistic description of the space distribution of the sources, and so I'm not sure I understand. We have tried different models. There are published description of pulsars, pulsars and supernovae, and description of spirals. So actually, in some sense, I've been comforted from the fact that the sensitivity to this is less than what I feared.
Mm-hmm.
And this is because actually the horizon of this gamma ray observation is rather large. Is of the order of many kiloparsecs, of the order of 10 kiloparsec or so. And so you are not seeing the very near structure of the arm which is clothed to you, but you see a reasonably larger piece of the galaxy. And so calculations done with a spiral model, with a smooth model, give estimates which are not too different. But okay. Certainly, actually, I must say this is, but I lost a lot of time. It's fascinating. This question of the spiral structure of the galaxy is really fascinating. It's a beautiful subject, poorly understood theoretically, and still very imperfectly known observationally. But this is actually relevant when you're trying to understand, to make sense of all of this.
Okay, thank you very much.
Thank you, Dmitry.
So there's next question by Zhen Kao. Please go ahead.
Yes. Hi, Paolo.
Hello.
Okay, very interesting talk. And actually, we had a long, time prediction, so I missed the first part of your talk. But that's okay. And the main part actually is there. I already got it. And I think Dmitry just asked your question. Seems to be this is my first comment. So much simpler than what you answered, I think. He is asking maybe just a simple geometry effect. Have you taken into account in your estimate of number of sources? This is my comment, first of all.
Yeah.
But I want to go to the point you made, just about this difference between AS gamma experiment versus nozzle experiment. I think that this actually is deeply associated with what you are talking about about this unresolved sources. This is actually the problem of the sensitivity of the detector. Once you have more sensitive detector, and then you will see more sources, right? This is very simple. So if you have less sensitive detectors, then you cannot resolve the sources, and then you will count them into the diffuse gamma rays. So once you have, my point is that if you get a really sensitive detector, and this unresolved contribution will be smaller and smaller, right? So this actually is give us a way, if you look at this this direction, we know very well to see what is the difference between AS gamma experiment versus nozzles experiment, and actually that tells you use the sensitivity of these two detectors. They already tell you something about this, the unresolved sources. I didn't do any calculation yet, but I just, it's my impression. Probably we can get some idea about this unresolved contribution from a nozzle experiment as well.
Well, Jen, first of all, I'm honored to have you listening to the talk, and my congratulations for the. As you've seen, a large part of my talk was based on interpreting the remarkable data of LASSO. It's just a comment. Well, I think I already heard you making this comment. One point is that if you're summing the source contribution and the diffuse flux, this is does not depend on the sensitivity of the detector, because you will just put more sources in the unresolved component. So if I go here, well, you see this I should sum. So this is the LASSO measurement. I can sum the source measurement. I still do not arrive to the Tibet result, actually, I think. So this I'm a little bit puzzled by this. So this is again the point that, well, actually I should have discussed this more, but it's unclear to me if these black points represent the diffuse flux of LASSO plus the sources. I think these are still higher. I mean, a question, well, actually, I would have two comments that for me are important. One question is the idea of masking. Actually, the Tibet paper, discusses a limit on the contribution of sources. So there is, they claim, I think, if I remember correctly, the sources are less than 9% of the diffuse flux, which seems too little to me. But because they try, they're not resolving sources, but they look in the direction of sources and see how many events they see. But I think there are two questions that I would like to note. One is the question of masking. When you are masking, it's difficult to interpret masking, because when you mask, when you do masking, you do an average, which is not in the entire region, say from latitude from -5 to +5. But in the region that you have not masked, and so that region is a region a larger latitude, and the flux is smaller. And I think actually a part of this result is due to this, that you are really measuring the flux not from -5 to +5 in galactic latitude, but you are eliminating a part in the central parts. So I know it's very difficult, but it would be very desirable to measure the gamma ray flux, the total gamma ray flux, sources and diffuse. Also because actually what, and this has been discussed by several colleagues, eventually this separation between interstellar and source will get diluted at higher energy, because you have these particles will exit from the sources and you would have extended halos and so on. So eventually, I think when you're approaching PV energies, this distinction between sources and diffuse is become less clear. So it will be desirable to have a total gamma ray flux from a certain region, and then you identify some sources to clarify this question, because I think the question of extended halos will become very, very relevant. It's already very relevant and will become more relevant in the future, I suspect. But I would like, Jen, I would like very much to discuss more with this. Actually, this talk in some sense was prepared thinking of a possible discussion with you, really.
Mm-hmm. And actually, I saw Zhang Yi actually saying in the audience, but now I'm checking on the list. He actually made some estimation once we have this result. Once we had this result, and to see the difference of ES gamma experiment and the nozzle, and basically the conclusion was that this is due to the source. But what you said is this is not enough, basically, right? To explain
I think so. I think so.
Okay, so that's
okay. Well, I don't want
that
to
deserves more investigation for this. I think this is important.
This is
right.
Well, yeah. I would like to. I'm very glad that you're discussing this, because I think to clarify this question would be very very important. And Jan, let me make another comment. Let me from this figure that you can. I hope you can still see my screen. So this is the Hawk result, the Hawk result. The Hawk result extend to 100 GeV, 100 TeV. Well, okay, so this is a different angular region, but you can compare these angular regions. I expect that the two fluxes should be nearly equal. In fact, actually, these are well, this depends on the modeling, but there are reasons, you know, this the Hawk result is from 43 to 73 degrees. This is a larger region, should be a little bit lower, but this is also a question where I see very close to a discrepancy in the data. You know, to talk about this, but it should be interesting to discuss together also this region between 10 TeV, from 10 to 100 TeV. Of course, it will be also interesting if LASSO could extend to lower energy. I'm not sure why this has not been done, but still the Hawk result extend to 100 TeV, and I think a critical comparison. I find interesting to make a critical discussion of this.
Okay.
I think we should figure out some other time to do this you know, more detailed discussion. Probably this is not a good place to do this.
Yeah.
This is not
here we are entering a discussion about data analysis, which is outside the scope. Is
not a LASSO meeting, Paolo. Let's be a bit more general. And Jonathan, I have a comment.
Yes, please go ahead, Felix.
So Paolo, I appreciate your heroic efforts to bring some order in the stuff. And I think, as a personal view, it's of course everything you did is very important. It should be done, but let me just a bit pessimistic in a general sense. Okay, I was not thinking to talk about the instruments, but first, I think that comparing different instruments is making even life even more complicated. I mean, you just the instrument which is the most sensitive, most reliable, and then, I mean, to compare so many things, like you are asking about the Tibet. So what? We just took the spectrum to the direction and the signals bubble and decided that is the diffuse. For just depends. I mean, what we do, and there are many other issues like Hawk is not even measured points. It's just there's a fit of that, so it could some impressive. So I think we should be a bit careful trying to explain different experimental data, and especially the if they are talking about large-scale structures. And this is the diffuse background, for example, comes from partly from unresolved sources. This is a common in astrophysics, but also in gamma ray astronomy, like diffuse extragalactic background, it is unresolved point-like sources. Here, situation even more complex. They are not only even unresolved, but their structures are so big, they overlap. So how decide which is coming from the source? And now we are absolutely sure that around the sources, particles propagate very slowly. So a lot of gamma rays were produced, diffuse gamma rays, but produced close to the sources. So I think it's not hopeless, but it's quite difficult. And in that sense, I don't like to hurt any other experiments, but Lhasa is superior in the sense, not general, it's not only this is big, because Lhasa is very sensitive to low brightness. This is, I mean, it removes background, and you could see that, like you detect pure gamma rays. It's extremely sensitive to low brightness, which is not the case, for example, Cherenkov telescope. So, but anyway, I did like to comment on that, this long discussion. I just now want to comment on the sources. So, I mean, to take all sources together, it is quite risky, because not because, I mean, there are general problems we know. I mean, the apples and the oranges we should not mix up. But here situation even more complex. I mean, in astronomy, for example, you do this how to call it, the population studies, right? So there are stars, just for example, right? So stars, everything depends on the temperature. You have a high temperature and abundances. So it's easier to some extent. Hot stars, not very hot stars. Here, maybe close to the stars could be pulsars. It's more or less, how to say, is could be, you could calibrate, because everything depends on the spectrum of in the pulsars, there's a curvature radiation. More or less, we can take pulsars as one source population and discuss them. Then comes other sources, and the other sources could be leptonic, could be hadronic, and all they could have different spectra. And not even if you assume, as I mentioned, if you have absolutely the same injection spectra, still the particles propagate. And propagation, even you could assume standard propagation, but then still you could find completely different spectra. Imagine you have the accelerator and you have a cloud at some distance. Depending on the time when accelerate particle, depending on distance between accelerator and the cloud, and depending on diffusion coefficient, you could see any spectrum in the cloud at the time. It could be extremely hard, it could be extremely soft, etc. So this is, we have to understand how they are formed. I could say even more, even you go individual sources like supernova remnants. Acceleration depends strongly on the environment. So it could be completely different spectra. So moreover, now we know that all these E-2 type spectra were, let's say, to be polite, but it was wrong in the sense because it is a steady state, ideal DCA, the prediction, when we know it cannot be -2 from cosmic ray data. And now supernova remnants theory also says in ideal steady state could be -2. So, and then spectra could be also different just inside the supernova remnant. So injection spectra could be different. You see, so many things are. Of course, they are not hopeless. For example, stellar clusters is better situation because these are continuous sources. It's terrible when you have the burst-like accelerator like supernova remnants, then you will be lost. I mean, analyzing what spectrum you expect inside the supernova remnant, outside in the environment, and then the clouds. So that I think I don't like to say that you should. It should be done what you did. Absolutely, this is no doubt about that. But I think we should be a bit careful mixing all different type of sources. And I said gamma ray astronomy has a very specifics which the others don't have. This is gamma rays are produced by particles accelerated and the target. So in stars, you see that just plasma, I mean, you detect. So, and depending on this, it's 2 components. And the second component contains propagation, which completely mixing up things. I'm not thinking of the propagation globally in the disk, that is more or less fine, all these Gall probes or these other concepts. But if you are near the sources, propagation makes things quite different. So there are, of course, good news. I mean, more or less all spectra from the stellar clusters we see, it's like E-2, 2.2, 2.3 type spectra, but for supernova remnants, it's more complex. So, sorry, I just even interrupted you. I should note at that time. I just want to say this is, I think we should be, if not pessimistic, but very careful. So, source acceleration spectra, propagation, and after that, bias with detector sensitivities, and even unresolved sources is much more complex for gamma rays, especially highest energies, because we deal not only unresolved, not detected sources, but we deal with huge sources, and all they are overlap. I mean, this is the case. So when you like to relate to the, and finally, again, let's be a bit to be now optimistic, saying we know everything. We don't know the cutoff energy, and it's clear cutoff energy could be different. And all we are talking very often about power law spectra, but power law is a cutoff also is a power law if you don't have a very long arms. Like if you do it within 1 decade, power law combined with the cutoff combined with power law gives you different spectra. So changing the cutoff, you could get completely different spectra, at least at highest energies. And cutoff is so sensitive to accelerator. So then you have a zoo. So again, just to finish, I'm absolutely sure it absolutely should be done, what you did, and this is should be appreciated very much, because in my view, this is a hell. I mean, just to go there. I mean, how to survive with this, but someone should do that, and I think it's really absolutely necessary. But still good to be a bit skeptical about this getting answers. And so that is all what I want to say.
Yeah. Felix, thanks a lot. Let me just say, I share a lot of your concerns, and I think they're well motivated. I still think
specifics for gamma ray astronomy. It is it is common for astronomy. It's difficult, but in gamma ray astronomy and these highest energies is especially difficult. So that is, yeah, we could only demagogically say we need more data, but believe me, I mean, or we need a more sensitive instrument, but believe me, if we'll have a 10 times more sensitive Lhasa and we'll have 10 times more data, I still could be pessimistic for this specific topic. But I said it should be done. This is no doubt about that. So where I can be optimistic, I will be optimistic with the individual sources to go, to analyze, and strong sources. So in that sense, my last comment about neutrinos, be careful with neutrinos. I mean, these are different level. I mean, so this is what they call it is artificial intelligence spectrum. I mean,
well,
you know, it's more sensitive.
It's a pity that the neutrino evidence for the disk emerges only from templates.
Yes, so fortunately, Lhasa is not the case. No template detection is there, but Lhasa also have a problem for interpretation. I mean, this is so it's very hard work. I mean, we should be, but it should be started. And I think, as I said, I personally think it's great that you started this.
Well, I do think I don't want to comment. The discussion I actually would like to invite other comments. Let me just say I share your concerns. They're well described, and I understand them. I still see some merits in trying to make a kind of a global analysis about energy balance of the galactic sources and general properties. I think there are certain things that could emerge that could be interesting.
Yeah, I agree. You are more fair.
You don't want. I mean, you want to try to. Of course, I think I think again that this is wonderful science, and a very rich science where you have different objects of different nature, and you have to understand it. But then, actually, to try to make sense of it or at least to try, is something you should try to do.
No. This is, I said, absolutely. We necessary to do this work, and that is good. But just to have this in mind.
Of course, eventually you have just to say you have another topic which it's obvious, I think, to this audience. Eventually, these sources are those who generate cosmic rays, and so you should relate the sources to propagation and cosmic rays. So the other piece of multi-messenger astrophysics arrives, and so when we are waiting for Jen to tell us how the composition evolves and so on, and then we have to relate this to these sources. And
yes, you are right. But again, you just said many sources. There could be pulsars. So we should first at least try to separate which are these cosmic ray sources, which are not. And this is a big surprise that the pulse of Paolo's could go even after 100 TV, and still we are thinking that could be a related pulsars, then nothing to do with cosmic rays. So anyway, so we agree it's very complex. I call it a hell just to go in that, but it should be done anyway. Thanks, Paolo. Sorry, I think there's not a criticism at all. I mean,
but the criticism is well motivated, Felix.
Yeah. Okay, so I'm talking too long. So Jonathan, I think maybe could.
No, that's fine, Felix. I think I don't see any more questions, and we've been going for an hour and 3/4 now, so maybe it's time to finish up. Unless anyone has some last comments, questions.
So anyway, I'm really thanks a lot for those who resisted here. I was very unsatisfied of my presentation because, if you have comments, please write to me, and I'll be happy. I know that there are many. I can see many flaws in what I presented in terms and incompleteness, but it's a broad, difficult subject.
Thanks for your patience. We need some workshop to discuss all these things. I mean, that is clear now, right time. It's
right. Okay, great. So thank you again, Paolo, for the excellent talk. It's really great. And I believe we're meeting again in 2 weeks, April 3rd. Is that right, Felix? Let me just have a quick look.
Yes, April. No, Paolo, you should remember when it was your
April 3rd is the next
April
talk.
3rd, yes, because yes, April
Yeah.
3rd. And another complex talk, even more is a diffuse, more or less similar talk will be that, yes.
Right.
Yeah, April 3rd.
Okay, great. So thanks everybody, and we'll see you again in 2 weeks.
Yeah, thanks,
And
Jonathan.
apologies again from Reshmi, who was going to host but had another commitment and asked me to step in. So okay. Thank you.
Thank
All the
you.
best, everybody. Thank you.
Bye.
Bye.
Thank you, Paolo.
Thank you.